Oh my God. That's not us. We're in the Semaphore example, right? And last time we looked at the writer with shared memory but no semaphore, right? And we looked at the reader. So I think we went through the reader first. And that's correct, isn't it? We went through the reader first. And then we went through the writer that used shared memory but didn't use our bouncer, didn't use the semaphore. All right. And then I posed the question at the end, why the the count was what it was. So let's run this again real quick, and then we'll what do I call it? Semaphore. See. Okay, so we had our. What do I have? I have two tabs open on there. Yeah, so here's our writer with no semaphore. So that guy sits there and does his thing, and then we have our reader, which is the reader, the same reader we're going to use whether we have a semaphore or not. So that guy hit 10,000. Hold on. Am I calling the right ones? Okay, so that's correct there. Okay, now we're getting different, we're getting values that are dissimilar from this 10,000 value. Do just the moons align on this first one, or we just happen to get the same, I guess. Let's just timed it with context switching. All right, so the question here is why am I getting a different counter when I read from our shared memory that is not protected by a bouncer, by a semaphore? What's the rationale? What did we come up with? Probably has something to do with the semaphore, right? So what do we think? We open up the code here and we look at our writer, no sem. And we get down to where it's actually incrementing our count. So I think last time we referenced this guy as kind of like a ghetto semaphore, where we're kind of messaging, where we're saying, okay, well, what write is not currently complete. And if we go over and I just open the reader at the same time, that's not that one, it's this one. So this guy is where he sits there and waits for it to finally flip that single variable of that struct that's sitting inside a shared memory, right? So he's waiting for write to finally be complete because he doesn't want to read until he has actually, until it's his turn to read. So when it's finally his turn, when the write complete is set, So inside, oh, this was our error message. That's fine. So he's sleeping for, we decided it was what, 3 seconds last time? So he's checking every 3 seconds to see if whoever's writing has finished writing. As soon as they mark that they're finished writing, then what's happening is he's just going to spit out, this is what I think the counter is, right? That's what the reader does. Now the writer is spawning off a child process, right? So we have a parent and a child both competing over that shared memory. So that's this one here, writer no sem, right? So up top here, if we, this is where we duplicate the process. If our PID is greater than 0, that means we're the original. And what we should do is we should call this counter increment. Keep in mind that both this guy and this guy are the same place in shared memory, right? Identical places in shared memory. So ultimately, they're both going to call the same function, passing in that same total count variable. And total count is, what do we say? The default is 10,000 if we don't pass in any command line arguments. All right, so they both think they're going to do something 10,000 times. The parent's going to do their thing, whatever that is. The child's going to do it and then immediately end. So once we get down here, this is the parent waiting. Child's never going to get to this line, right? Child is bailed out. So the parent's going to wait until reading has completed, and then finally, did they spit out what they read? Oh, they just say that it was that the writing is complete. The child has finished. So what do we do inside the increment? Well, we're doing something. So both the parent and the child are setting write complete to nothing, to 0. This is that same place in shared memory, right? So you have 2 different processes, both going up and saying, this is a value of 0. Possibly overwriting the, well, definitely overwriting the other one, possibly, depending on how it ends up being scheduled, changing a 1 back to a 0. Possibly, right? All right. So then we're just advertising who's the one writing right now. All right. And if we look at our output here, we see both the parent and the child advertise themselves as writing. They both think they have the resource, right? Because all they did is they said, you know, my fake semaphore is the shared memory, and the only thing that had to happen in order, well, actually, they didn't even check to see if it was available, did they? They just zipped on in there and said, set it to 0. it's mine. You know, they're not incrementing, decrementing, nothing, just like it's 0, it's mine. So both the parent and the child, whenever they get access to the CPU for this thing, they're setting the same place in shared memory to 0. And then they're both spitting out. Let's see, can we even get a example where the child goes first? We actually do get an interesting thing here where the child finished writing first. But that's not consistent, right? So when we look at the output here versus the output here for the same process running, we're seeing the process scheduling, right? Whoever got the CPU time at the right time to finish up their count, whatever. So there's no guarantee. We have 2 separate running processes using the same place in shared memory that we'll call, in our case here, critical section, which I think you said last time, right? So we're treating the shared memory as our critical section. We have 3 different entities all trying to share this thing, and really 2 entities are competing for modifying that resource at the same time, which is what's giving us a level of randomness. So go back in here. So we just, no questions asked, parent and the child both grab the resource, just setting that thing to 0. Then they advertise, actually, this is probably the thing that slows it down the most. It adds the most randomness to it because IO is expensive. Writing something to the screen is expensive. If we took that out, we probably would have a more consistent count, would be my guess, just because we're not having to interrupt the CPU, because when whoever comes in first, I think we saw the parent pretty consistently came in and said they were writing first. So that means the parent was jumping off the CPU first every single time. Now the child was also then doing it, but then they have to get back in line, and there's no guarantee for multiple cores who gets scheduled next necessarily. All right, so then whether I'm the parent or the child, I'm going to do something total count number of times. And what are they going to do each time? They're incrementing counter. Counter is a local variable, a part of this function that gets initialized to whatever the counter originally was, keeping in mind that there's no guarantee that the child will call this guy here before the parent has already started their for loop, right? So there's a real possibility that the child could initialize their counter, and I'm saying it as if we're guaranteed that the child will go second. It seems like that's been the consistency, but we have two separate processes. One process may have already started changing the value of our shared memory pointer counter. So this guy isn't necessarily initialized to 0 for both of them. Should be initialized to 0 for one of them, okay, but not necessarily both of them. And then they're just saying, okay, I'm starting my write, marking it the same for the same guy. And counter is either 0 or something greater than 0, because inside this loop, we are incrementing counter and then setting our shared memory to that new value of counter. So now you have a level of competition, right? So let's say that both the parent and the child come into this section, and let's just say it was process scheduling seems to line up pretty well. Let's just say they both did start with a count of 0. Seems likely, right? That it'll start with a count of 0. So now they're in this for loop, and the loop is spinning through. So let's say maybe the parent's taken counter to 50, whatever it is. And let's say, and each time through, they're overwriting counter to be, 48, 49, 50. And now the child comes in, they maybe only got to 25, right? 28, whatever the number is. Now they're overwriting that 50 with a 28. So we haven't synchronized. We have this one counter and we have this one place in shared memory. Okay, that's so our shared memory counter, this one integer that's in shared memory. Both the parent and the child are setting this guy to a value. They're not incrementing this value directly. Instead, they both have their own local counter that goes from 0 to 1 to 2 to 3 to 4. There's no guarantee that those guys are synchronized, right? Parent might be at 50, child might be at 28. And what's the value of our shared memory pointer counter? It's going to be whoever overwrote it last, right? So we might have 50, 28, 51, 29, so on and so forth. So you have both of these guys making changes to that same counter. How long are they going to do this for? Well, they're going to do it total count number of times, again, which is a local variable. Okay, so they're not doing it while this guy, while this guy is less than 10,000 or whatever that global variable was for that. But even that wouldn't save us, right? Because you might bail out of this for loop when one guy sets it to 10,000 and the other one sets it to, 9,987, and he's not done. Eventually, it does get to 10,000 though, right? Because whoever wrote last will write it to 10,000. So that's why it's always going to be 10,000 on the parent side over here. It's always 10,000. But we aren't necessarily, realistically, we've changed the value 20,000 times. Is that a fair assessment? We changed that value 20,000 times. Sometimes we overwrote it with the same value, but we did change that variable 20,000 times because both the parent and the child did this 10,000 times. All right. It's always going to be 10,000 in the end over here because whoever wrote last did it on their 10,000th trip through there. So their version of count is 10,000. So they overwrote the shared memory count to 10,000. All right, so that's why this guy is consistent. Let's just make sure we're not doing anything crazy on this. Now notice over here, we are sleeping every thousandth of a second, let's say for 1 second. What is this forcing to happen? What do you think that code there is forcing to happen? In English, it says it's sleeping for 1 second. I'm asking, or for a thousandth of a second. Well, sleeping for 1 second every 1,000 iterations through here. So it's doing this 10 times, right? But from an operating system perspective, what do you think is actually occurring here?
Are you trying to block the resource or block the process from accessing the resource?
Well, but is that happening? So, well, let me ask a follow-up. How do you think it's trying to block the process from getting the resource? Both the parent and the child process both have direct access through shared memory to that resource.
The way I interpreted it was that you would try to offset the executions of each process, maybe.
Okay. It's possible we're talking about the right thing here. So this guy right here doesn't do anything with protecting the resource, right? We're not locking down that place in shared memory or anything like that. It's a free-for-all. But when we tell a process to go to sleep, similar to how I mentioned up here where we're doing IO is expensive and you get bumped off the CPU. This is kind of a forced way where we're very, very, very likely forcing a context switch, right? Sleep is saying, I have nothing to do for the next second. Operating system's job, one of its jobs of the CPU scheduler is keep CPU busy 100% of the time. Rarely does it meet that goal, maybe for games or rendering or something like that. But generally speaking, the CPU scheduler is going to say, hey, if there's a process running on the CPU that currently has nothing to do, get that off the CPU. Get something else onto the CPU. So what is this effectively doing? It's forcing a context switch. So by all intents and purposes, we've forced 20 context switches, effectively, hopefully creating at least an artificial back and forth between the parent and the child. Does that make sense? That then creates let's call it the guarantee that we already knew we changed the value 20,000 times. That's just math, right? But it's at the very least creating the guarantee that we very likely had counter going backwards sometimes, right? Where, it was a 50, then it was a 28. It was a 65, it was a 51, something like that, because these guys are, this guy maybe was up to 230, and then he got put to sleep. This guy caught up, and maybe he's at 560, and then this guy says 231, 232, 233, as this guy got kicked off, and he's back on, and he's at 562, 563, 564. So we're creating probably a guarantee of these guys having numbers that are not sequential, all right, because we're not protecting that central resource, even though we are guaranteed that the last value on the right is always going to be 10,000, because both of those loops go to 10,000. So whoever wrote last is going to write the value 10,000. All right. That's why that always happens over here. But if we go over to the reader, when does the reader actually write out the counter? So, all the rest of the stuff up here is very similar to the writer, right? So the reader down here, when does he actually say, here is the counter, the shared memory counter? He's doing it as soon as he can get past this gate, right? So this is our fake Semaphore thing. I guess we're not protecting the resource, but we are under what circumstance would we get to this line when both, when one of parent or child is still counting? How is it possible that we can get the line 66 here when over in the writer, either the parent or the child is actually not done? How does that occur?
When one of the processes finishes and the other one's like sleeping, that the write complete is changed to 0, and this
Yep.
could start reading in between that time.
Yep. So the idea here is that we actually have a race condition. We're forcing a race condition by operating at multiple seconds as opposed to, you know, nanoseconds or microseconds or something like that, where things are happening really, really, really quick on the computer. Not that it's not still possible, but we're kind of forcing the issue here, right? So this guy right here, it is entirely possible, since he, every 3 seconds, he's going to sleep and he's coming back around and he's asking this question right here. Is write complete equal to 1? He's going to bail out of this while loop as soon as somebody says they're done writing. And we do have that possibility that either the parent or the child, whoever finished first, has said, I'm done writing. And this guy comes in and says, they're done writing, and goes down and reads, when then the child finishes the count. Does that make sense? So if we come back in here like this, here's my read. That's actually interesting. Why would it be 10, 8, 90? How's it ever getting that high? Shared memory counter should never get above 10,000. Isn't that our starting point value over on writer? Total count, total count is 10,000, not 20,000, right? Yeah, default is 10,000. So we're doing this 10,000 times. Counter starts at, okay, yeah. It goes back to what we said earlier, is we're not guaranteed that this is a 0. In fact, if we look at this guy, it appears like the child probably got to 890 before the parent, well, the parent got to 890 before the child started their counter, probably, assuming the parent got the CPU time first. So the parent started cooking, right? It started saying, we're going to 1 to 2 to 3 to 4 to 5 to 6, overwriting shared memory each time. And then finally the child gets CPU time and comes in and says, okay, I'm ready to initialize my counter. So right here, he says, my counter is equal to the current value of counter in shared memory, which in this case was 897, whatever the number was. Good.
So in the reader, if you either took out the sleep function or made it very small, you could get something like 10,000?
Get something under 10,000. Possibly. Yeah, because then you're exaggerating the, so he asked, for those of you online, that in the reader, if you make the sleep function very small or non-existent, right? Non-existent is probably the best way of doing it. It's super inefficient, but we're just, you know, you're asking question after question. You know, it's like, is it ready? 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 With no waiting in between. But then there would be that possibility that we've created that race condition. If I go back over to the child here, where the child, or I'm sorry, the reader here, the reader is convinced that one of the writers has finished, and he falls past this, but before he reads from it here, the other writer has written a value that's now less than the total value. Does that make sense? And if that's the case, he could have a value less than 10,000, right? Because what it's going to do, all we're doing here is the reader saying, look, as soon as somebody has finished writing, as soon as I think somebody has finished writing, really he's hoping to say here that is everybody finished writing? That's what he wants to say here, but he really isn't asking that question. He's asking the question, is somebody finished writing? All right, because over here on the writer, they only flip it to 0 once at the very beginning. They're not flipping it back and forth or anything, right? They're not, I mean, if they did that, they could do something like, let's set it to a 0, let's change it, then set it back to a 1, letting somebody else get in there, which then would cause the reader to read through more quickly, right? And say, okay, well, your answer 17 or something like that, but go ahead. No, because we're not doing it on counter, we're doing it on num times. So this loop goes through total count number of times. So this is going to do something 10,000 times, but the value of counter was initialized to whatever the current value of our shared memories counter was when it started.
So that's what I'm asking is, would it have to be like both start at 0, like they start at the same time, for them both to be initialized to 0, so it's not.
You mean like in the ideal? Yeah, in the ideal world, maybe. In the ideal world, if you have two different processes that you want to kind of work in parallel and you want to make sure they both start with the same number, you might choose to synchronize this value where you don't actually let either of them continue on until they both have grabbed the initial value. So you could actually use it, we'll look at the semaphore in a minute, but you can actually use a semaphore to protect this specific resource. You know, you can say, I've read from count to get my initial value. And then, so let's say parent reads from count, gets a 0. And then the parent now can't go on. We can protect the rest. We can call this, the rest of this, the critical section. We can say the parent can't go on and start their counting until everybody else has said, I've grabbed the, we've synchronized our watches. We've all grabbed the initial count, which should be 0. Does that make sense? Okay, so let me make sure I understand the question you're asking. As it is right now, there's no guarantee that the parent and the child both set their local variable counter equal to the same value. Okay, this line right here does not guarantee that. Because whenever the parent and child get here to line 104 in their respective programs, they're going to grab current value of counter. And current value of counter changes inside this for loop. So you're at the mercy of, did one of them kind of get a head start or not? So we get that. We're good there? Those two things aren't necessarily guaranteed to be the same right now. These are two completely separate processes that are scheduled by the CPU that's out of our control. And it's entirely possible if we just, say that it's possible that the parent gets the count to 100 before the child even gets to this line. That's possible in the current setup because the shared memory counter is the same place in memory for both the parent and the child. They both are looking at that same number. And when the parent gets to their line 104, they're going to say, I'm going to initialize my local variable counter equal to whatever that guy says counter is. And we can assume that for parent, let's say they got to go first, it's 0. But then the child swoops in, and maybe the child swoops in quick enough that the parent hasn't gotten to this line for the first time yet. And if that's the case, the child would also grab a 0, right? You say, the value is currently 0. We lucked out. But right now, this code does not guarantee that because the parent could have said, okay, I got my 0. Now it's a 1, now it's a 2, now it's a 3, now it's a 4. Then the child swings in and says, I got a 4. Like, I'm just reading whatever's in shared memory. Okay, there's no guarantee. We haven't protected that value. The operating system is that they're doing whatever they're going to do in terms of scheduling those processes. And now we're at the mercy of how many loops through did whoever got there first get to do before we read that initial value.
So if they both happen to start at zero, even without some sort
Yep.
of, is it possible that when you end it, you have a number less than 10,000 because of the rewrite?
Okay, her question was if they happen to start at zero, we just hard code this to a zero. If we just say, look, it's a zero. Anyway, you cut it, it's a zero. I'm not even going to read from it. It's just a zero. When we're done, is it possible for it to be less than 10,000? It depends on what you mean by,
Like if one-
from whose perspective?
Right, the second one.
The reader's perspective or from the reader's perspective, it is possible. Because from the, so she's asking is from the reader's perspective, if I come over here, is it possible that this value here is less than 10,000? The answer is yes, because of race conditions. We know that if we're here, one of the parent or child has counted to 10,000. That's happened, right? So at some point in time, this value right here was 10,000. But that doesn't mean it's still 10,000. Because if the other dude was dragging behind, right? Possibly, let's say, if the other guy was dragging behind, then it's possible between when we exited this and got to this line, this value was changed by the parent or the child, whoever was dragging behind on the other side, who hadn't got to 10,000 yet and just wrote 9,874. And then this guy could potentially read a lower value than that. But we also saw it could read a higher value than that because it's going through total count number of times, not necessarily until count equals 10,000. It's always, the parent and child are always going through 10,000 times, but their starting points might be different. By our example here, it was like 800 and some odd was when the child presumably started. So we actually got 10,870 or something. Yeah.
One interesting thing I noticed that one time where actually it was exactly 10,000 is when the child finished first.
Okay.
So I don't know if there's a correlation to that, or does it not? If the child finishes first, like complete skill set to zero right away? Is that a something?
Okay. So the one you said on the one time that you did notice that it was.
So you can go to your terminal.
When it was the same, I was wondering why.
Yeah.
Like, how did the moons align? So if we're in here and the child finished writing, no, I mean, shouldn't make a difference. Whether you're the parent or the child, you're flipping the switch to a 1. So, yeah, and we're adding the same delay here with IO delay. Yeah, I would just say CPU scheduling, moons aligned, buy your lottery ticket type situation. But it does create an interesting thing. These are things that are out of our control as a programmer, right? So this kind of goes back to this idea of what is systems programming. We're at the mercy of the operating system that we're writing software for, and it plays by its rules, and we don't have control over that. If we need to protect a resource, we better protect that resource. Yeah.
I think I remember us returning earlier in the code if it was a child rather than a parent.
Yeah. But we've still flipped the switch already. Yeah. So the only thing that we did up there, he's referencing higher up in the code, the child bailed out where the parent finished this function. So they both call the same function. Up here, the parent doesn't bail out. The child, when their function finishes, they bail out. So the only difference is who gets to this line, right? So it's always going to be the parent who gets to this line and waits for the reading process, the other process, not the child, but the process that's doing the reading to finish. And we only got one of them. So we're guaranteed that we're not protecting the resource, but we only have one dude we're waiting on. We don't have a possibility if somebody sets the read complete to 1 before it's actually done being read. Yeah, so this is the parent always saying, I will wait for the reading process to finish doing their thing, and then I'll spit out, we're done. And if you want to see that in action, if we call the writer nosem, it doesn't matter how long we sit here. It will not finish. It won't say writing process complete. Even if we sit here for a month. At this point, both the parent and the child have finished. And now the parent is sitting there spinning, waiting for our reader process to finally set that reading complete in the shared memory. And that's what will happen over here. So now we have reading complete here. We go back, it'll now be complete. Because it just got through this code right here. We were just sitting there sleeping for 1 second over and over and over and over again until somebody finally ran that other process and the read did its thing.
Can you say that the parent is not always guaranteed to run first? Is that a true statement?
That's a true statement. You're at the mercy of how the operating system schedules these processes. Now, having said that, I would say it's probably very, very, very likely, even potentially guaranteed, that the parent will run first because they are getting in line first. But especially when you get into operating systems that are supporting multiple processors, if the parent gets into, just because somebody walks into McDonald's before somebody else doesn't mean they'll be able to place their order first. Depends which line they get into, right? They might be in the slow line, where somebody, they're ordering for, a bus or something like that. But I would say from a systems programming perspective, the short answer is almost nothing's guaranteed. If you want something to behave a certain way, you have to take the extra step to make it behave that way. You can't rely on luck of the draw from the operating system, or this is probably more akin to when you think about back to beginning programming classes. If you look at most programming languages, especially older languages like C and C++, when you define an integer a, and if you put no value in there, then you try to print it, it'll print out probably a 0. It does have a default value. Okay, but I've taught you not to rely on a default value. There's no guarantee that the default value will always be 0, even if it happens to always be 0. You never know, you might be on a different architecture, or a different operating system, or a different compiler where they've just, decided to screw with you and they set the default value to -7. Just because. If you want it to be a 0, you put a 0 in there is the idea. So the same thing's true here. There is entirely a possibility in the current Linux kernel that the parent will always get CPU time first, depending on how the fork system call is written and how it's scheduled and that kind of stuff. That's entirely possible. But if you want to control that mechanism, don't rely on happenstance. All right, so do we see what's going on and why these things can be kind of out of sync without having something protecting the shared memory? All right, so now let's go look at the Semaphore version of this. We don't have to look at the reader. The reader's not changing, right? The reader is still always going to do the same thing it's doing now. It's going to say, look, I'm not going to start reading until I know it's done writing. Where it's done writing doesn't matter to me as the reader, because from my perspective, it's done writing whenever that 0 becomes a 1. Or not even, we don't even assume it's a 0. We just care that it's not equal to a 1. So as soon as whatever it was becomes a 1, that from a reader's perspective, I'm now convinced that whoever was writing to it's done and now I can go do my reading. So if we look at the with sem, I think we'll see everything up here is pretty similar. get our shared memory, attach it, call fork, call those same functions depending on who we are. Only the parent gets down to here because the child returned. So same exact code up to this point. But now inside of our shared memory, we're now having a semaphore. All right, so we're going to create a semaphore. So we are going to have a SemID using SemGet. And we put in here, here's the number of resources we're protecting. One, that one place in shared memory, right? That's our resource that's in question here. All right, so we'll create it if it's not already created. So now we have the SemID. So if SemID is greater than or equal to 0, we must be the first process. What are we going to do? We're going to set it to a 1. We grab it. This is an atomic operation. Actually, this is the atomic operation. That function there is the guy that acts as if it's atomic. This is our setup for that atomic operation. All right, so if our SemID is greater or equal to 0, SemID came from our SemGet. So this guy is going to get us a ID. And again, this is also going to behave as an atomic operation. 2 people cannot get a semaphore with that same key at the same time because this guy protects against it. The way it's written, it acts as if it happened in a single CPU cycle. So SemID is guaranteed to be different for the 2 processes. All right, so I'm going to fix the formatting a little bit as we go through this. Bad things happen with our semaphore. What's this else here? This else here says, you know, that somebody else already has that process, or some other process already has the semaphore. They already have the resource. All right. So now we'll be on time. Oh, we're okay. This will get us to where a good stopping point. So we'll have our error. Somebody else already has it. So what are we going to do? We are the other process. We'll spit out that we're the other process. We're going to go ahead and try to get it. This guy is going to block until we finally get it, because it's an atomic operation. And when we say we want to get the semaphore, what we're effectively saying is I want access to that resource. And this guy won't let us. This is the bouncer. He's holding you back, holding you back, holding you back until they finally let you through. Okay, because somebody else is currently using the shared memory. All right. So remember, we're either the parent or the child here, right? So we're either the first process or the second process. And one way or another, we need to get through this gate. What do we do once we're through the gate? Where am I incrementing? I will go through it in more detail next time, but once one of the 2 gets through their gate, and this is where they're, you know, locking the semaphore, they're getting it, they're operating on it to lock it. They go from a 0 to a 1. These are all atomic operations. When you get a semaphore, that gets you access to it, then you can set it to a 1, which locks it, but you're the only one who has access to it. So if you have access to it, that means somebody else is being blocked by a bouncer. All right, so these are just semaphore operations that are happening in here, but only one guy gets the resource. Once he has the resource, he gets to do his thing. He'll fall down past this. And what will he do? He's going to go ahead and set write complete to nothing. We're asking about what our PID is to find out are we the parent or the child. We're going to go through num times, incrementing counter each time, every 1,000 times. So we're doing the same stuff we did before. And then we'll set write complete to 1 and bail out. Remember, our reader is still looking for write complete to be 1. Now up here, we either got the process or got the shared memory, or we didn't get the shared memory. If we didn't get the shared memory, then we have to wait for it. The reader is always going to read from that 10,000 because I don't think this guy gave the resource back. We'll confirm that next time, but I'm pretty sure he doesn't give the resource back. So it basically becomes a race between the parent and the child to see who got the resource, who did the counting, and now the reader is going to read the same value each time. All right. Although actually, if I remember the output on the reader is always 20,000. So actually the reader doesn't get to read until after the parent writes all their 10,000. Then the child comes in and grabs a 10,000 as their starting point. They write all of their 10,000. Then the reader reads the 20,000. So that's actually what's happening. They are locking it down, finishing, giving it back, letting the child come through, finish their thing, which then the child is setting it back to a 0 for their write complete and going on and doing their count from scratch. The reader can't move on yet. That makes sense? So this allows us to protect that critical section. So we'll walk through the details of how we're locking this down next time. But at the very least, we see at the high level how a semaphore is protecting access where only the parent or the child has access to that shared memory for however long we want them to have access to the shared memory, which in this case is this for loop that runs through 10,000 times. And the other guy doesn't get to interject. All right. So no homework. We don't have class Friday, right? We don't have class Monday. So the next time I'll see you is next Wednesday, a week from today. Have a safe Easter if you're traveling somewhere, and I will see everybody on Wednesday.